Okay, folks, so let's move into chapter 3, the chapter 3 practical, which is on linear image transforms. So, some there's occasionally been confusion about the difference between linear image transforms and linear image operators. So, just to kick this off, the linear image transforms refers to the mapping of an entire image into an alternative representation. The linear neighborhood operators are simply operators that work locally on an image. So if I talk about linear image transforms, I'm talking about mapping the entire image into the transform domain. Okay, so to do this, the first thing that we're going to look at is complex numbers in NumPy. So NumPy, the very important Python library for numeric computation, allows us to represent complex numbers in a fairly natural syntax. So we can create complex valued variables. So here's A and here's B defined just using lines of Python. We have to make sure that J ideally isn't associated with some other variable, but honestly, I don't know how Python deals with that, but I tend not to use J as a variable in my Python coding anyway, and that's probably good practice. So multiplying A by B, you would get 5 plus 0J, given these definitions here, and you should just confirm that you're happy with that, and there's nothing surprising there to you. So you can you've got a couple of NumPy functions that can be used to get the absolute value and the angle of complex numbers. So np.abs and np.angle. And also you can get the real and imaginary parts separately out of a complex valued variable by simply using dot real and dot imaginary, and those give you the real and imaginary parts respectively of a complex variable. So that should be fairly easy. Okay, in the first bit of this practical, you're simply really looking at an exercise that was set in chapter 3 involving exactly the same image with exactly the same definition of basis images. And so this is also repeated in this practical to make sure that you do this exercise and understand what's going on here. So the important thing to remember is that in using these basis images and this little definition of an image or an image space to map into transform space, we are not doing standard matrix multiplication. We are instead using the inner product or the matrix inner product between matrix and matrix. And what that means, if you want to think in terms of in terms of standard matrix vector algebra, what you're doing is unraveling this image matrix into a vector of 4 by 1, and you're unraveling each of these basis images also into a corresponding 4 by 1 vector, and then you're doing a dot product in turn between this image and each of these basis images as vectors, dot products as vectors separately. And that's also described in the notes. Why do we preserve this in the form of a 2 by 2 image if we're really doing something that is treated as a dot product? Well, it's because by preserving the basis images in their two-dimensional form, we can see relationships between the values you get in transform space and spatial structure in the image. And that's the main reason for introducing this extra operation. But you should make sure that you understand what I've been talking about in mapping from this image using these basis images into transform space. So that's the thing that you must do as a first exercise. There's a bit of funny formatting on my version here. I can't figure out why this is happening. It hasn't happened before, but I've discovered that if I go into here and just fiddle around with the text a bit, for some reason it begins to magically work again. So well, this is still not working properly. Anyway, so you may want to read these on your own version of the. Yes, this is rather annoying. Let me just see if I can do anything here that will get this working. Yeah, probably not. Let's just try that, see what happens there. Yeah, okay, ridiculous. And let's do the same thing here. Okay, so these are now correct. So this is the forward mapping. So this thing represents the the uh, the inner product between matrices, which again it's the equivalent to the Hadamard product between each of these, and then summing the Hadamard result. So Hadamard product means you take each pixel in your first matrix and multiply it by each pixel in the second matrix, and that gives you a result. If you take a sum of all the elements in that result, that gives you the same as the matrix inner product. Okay, so you should run through this calculation and make sure that you get exactly the same result that you have in the notes. And until you get that, and until you do that and work through that and make sure you know how to get the right result, then I would not be confident in going any further with this practical. So make sure you do this exercise first and you're happy with it. Also make sure that you can that you confirm you can go backwards using this equation 3.2, and also, or exercise 3.2, and also make sure that you can interpret this equation whereby you're blending these basis images with a proportion or inner proportion determined by these scalar values here of transform space. So if you interpret this correctly, then what you're doing is you're adding three matrices together. Okay, the fourth matrix, so B11, will actually have a weighting of 0. So make sure you understand how this expression differs from this, and just be clear about interpreting these. So these equations are, strictly speaking, all correct. You need to just make sure you understand what the difference is and how to relate the equation to the operation you're doing on paper. Okay. There's something here about estimating computational effort. So the main thing to recognize is that in working this out, key thing to click in your minds, in realization, if you like, is that here the number of basis images is equal to the number of pixels in the image. So in other words, the definition of a transform adapts itself to the size of the image. Okay, and that's true for most of the linear image transforms, and it's very easy to see that, because if you're thinking in terms of this Hadamard product, or sum of terms of Hadamard product between this image and each of these basis images, then the number of pixels within here, well, it scales in two ways. So first of all, we have the number of basis images, which is 4, and then we have the size of each basis image, which is also 2 by 2. So in other words, the same size as this image, as the input image we're transforming. So there are two factors here that give us a scaling. If we go up in size here to, let's say, a 3 by 3, what would happen is, not for all transforms, but for most linear image transforms, we would also increase the number of basis images accordingly. So if I had 9 pixels in my image rather than 4, I would have 9 basis images. Furthermore, each of those basis images would also be bigger, would also be 3 by 3. And so you can begin to see that as you scale the size of the image, let's say we restrict ourselves to square images, and we call that size n. So in this case, n is 2, because we have 2 rows and 2 columns, so it's an n by n image. Then as we go up in size to n equals 3, then we go up in computational effort by a factor of 4 with respect to n. Yeah, so the transforms would, expressed in this way, scale effectively or implicitly as n to the power of 4. The computational effort required to go from image space into transform space goes up as n to the power of 4. So make sure you're clear on that. Okay, so once we get through that first bit of just revising stuff we did in the lectures, we then start playing around with real image transforms, and we're going to start by looking at the head image, nice MRI image, and which is of size 128 by 128, and we map that into discrete Fourier space, two-dimensional discrete Fourier space, using a command like this. And so what's going to happen is that we don't have to explicitly use the basis images ourselves or write the algorithm ourselves. We're making use of a predefined library. And most numerical libraries are going to have the equivalent of a discrete Fourier transform in 2 dimensions, in fact, in n dimensions. So this is not unusual, and these transforms are very, very widely used. The discrete Fourier transform in particular. So this maps this maps us to discrete Fourier space, which is represented by capital X here, as distinct from the original image lowercase x. And if you have a look at some of the values of x, so to do that, you can just take arbitrary values. So let's just see how to do that. Well, it's pretty easy. So this is a two-dimensional array. So if we just did x, let's say 0. I forget how to address in 2 dimensions now. How embarrassing. Let's try that. Okay, so there's one value, and this is in fact corresponding to the biggest value in transform space. It's purely real because this actually represents the sum of all the pixel intensities in the image. It represents what's called the DC term of the image x, and that value there, 701110, we should also be able to get if we did np.sum. Well, let's just drop this. Okay, let's drop this in the next cell to see where that comes from. If we do np.sum of little x, and see what we get for that. So we get 701110. So x00 actually corresponds to the discrete Fourier transform result corresponding to 0 frequency or zero rate of oscillation, either in the x or in the y direction. So if we're looking at a frequency which is at 0 oscillations or cycles per pixel, then we have effectively a cosine and a sine of 0 cycles per pixel, and cosine of 0 is 1, and so effectively what we're getting here is just we're multiplying the pixels by the Fourier kernel, which is e to the j times the frequency, or e to the 2 pi j times the angular frequency. And so since the angular frequency is 0, we just have e to the 0, which is just 1. And so what we're doing is we're summing just over all the pixels in the image, and that's it. And that's why that first 0 term is so big. If we take some other terms, we're actually looking at terms that correspond to oscillations. So let's take 1, 2, and there you get non-zero imaginary parts, and you get a fairly uninterpretable number, which is the represents the magnitude of the real and imaginary parts of the coefficient in Fourier space, discrete Fourier space, and that coefficient, when multiplied by, would be multiplied by the wave of the corresponding frequency if you wanted to reconstruct the image x from its Fourier space representation. But again, that's not something we would do manually. We do in fact do an inverse discrete Fourier transform somewhere further down. But the first thing we're going to try to do is to visualize the space. So we've got a couple of issues here. in visualizing the space. And one of the issues is that the biggest value we have, as we've seen, that should be x dot max there. One of the things we do is if we look at the max and min values, we'll see there's a very, very big dynamic range in discrete Fourier space. And it's quite difficult to display that simultaneously and be able to see all the detail. So one of the things that we do is to, if we want to display this, we can try to compress the dynamic range. This is what the result looks like without doing anything. And we have two problems here. One is that the only non-zero value is up in the corner here, not very visible, and that's because Fourier space is wrapped. And then the second problem is the fact that the values are complex. So by converting them into absolute values, so looking at the absolute values of the complex numbers, and reordering Fourier space, then we get a bright region just in the middle here. So you can also, as I said, take the log of this to display something a bit more. So we could try, for example, np.log of this thing here, if we wanted to see a bit more detail. And so let's just do that. And that gives us something like this. So you can see a bit more detail because we've squashed the dynamic range down. Now you wouldn't use the log to do processing generally in Fourier space, except in extremely rare circumstances. So this is just something that we use for visualization. Okay, so I'm going to get rid of this to make sure that it's clear that that's actually the result that we should be happy with. Okay, if we take the inverse discrete Fourier transform, which I think is here somewhere. Yeah. So here it's being done here. And let's just see what that gives us. So, so we do that. And now if we examine what this result looks like, in p.shape, x dash. Okay, it's 128 by 128, which is the same as the size of the original image. However, if we take one of those values and just investigate them, so that's the value in the corner of the image, and what we'll see is that it has very small values in both cases, but this value is imaginary. I mean, it's complex valued, so there's a real bit and an imaginary bit. What does the original pixel at that location look like? So the original pixel at that location is 0, 0. So what we've seen is that we're not getting exactly the same values back when we take a forward and inverse discrete Fourier transform. Instead, there's a bit of numeric error. Now, in a very good implementation of the discrete Fourier transform, intelligently done, the libraries, a library would generally recognize that small error is due to round-off error and would be thrown away and just represented as 0, 0. But within NumPy, the NumPy routines, that isn't enforced, and so you have this very, very small residual that comes from the approximation error in trying to represent cosines and sines on a finite precision type of system to do arithmetic. Okay, I'm going to have to pause here because of someone at my door. So sorry, I was doing a recording. Okay.
It's done.
Recording? What? I think I paused it. I'm not sure. I'm not entirely sure what's happened here.